Okay, here's a thought to start us off. What if the space you're sitting in right now, the three dimensions that feels incredibly solid, so fundamental, what if it isn't actually the bedrock of reality?
Hmm.
What if instead it's built up from something far more abstract, maybe something quantum, something that emerges purely from, well, from the timing and sequence of events at the very smallest scales?
It definitely sounds counterintuitive, doesn't it?
No.
Because our everyday experience, everything we see and touch tells us space is just there. It's the
Yeah,
stage.
the container.
Exactly. We usually think of quantum mechanics, all that weirdness,
Yeah.
as happening within space and time.
Yeah.
But, many physicists today, especially in theoretical physics, are seriously exploring the possibility that space, and maybe even space-time itself, might not be primitive.
Not the absolute foundation.
Correct. It might be an emergent property, something that arises from a deeper, more fundamental description of reality, much like, say, the wetness of water emerges from H2O molecules, even though a single molecule isn't wet.
Okay, and that philosophical shift, that idea of emergence, is exactly where we're diving today. We've got our hands on a really fascinating paper that tackles this very directly.
A very specific angle on it.
Yes, it's called Geometry from Quantum Temporal Correlations, and the authors are James Fullwood and Vlatko Vedral. And their core idea is, well, it feels pretty profound. They propose that the familiar three-dimensional Euclidean space we all inhabit, it could potentially emerge directly from the structure of these things called quantum temporal correlations.
And they're very specific about where these correlations come from. It's not just any quantum system. They argue it arises from the correlations you find when you perform sequential measurements,
Right.
one after another, on a single, incredibly simple quantum bit, a qubit.
Just one qubit.
Just one qubit. The timing, the order of these specific measurements, and how their outcomes relate to each other. That pattern, according to this paper, could actually hold the mathematical code for 3D geometry.
Wow. Okay, so our mission in this deep dive then is to really unpack this radical idea. We want to understand what exactly quantum temporal correlations mean in this context. How could they possibly encode something like geometry? Why is this connection so surprising? And, what could it mean for how we understand the very fabric of our reality?
And there's a particularly striking finding they present right at the outset, which you hinted at.
The state independence part.
Exactly. The possibility that this geometric emergence might be completely independent of the initial state of the quantum system being measured. That's a key piece.
Which sounds wild. Imagine an observer somehow discovering the rules of geometry just by making these sequential measurements, without needing any prior knowledge about the qubit's starting point.
It suggests that geometric structure isn't tied to a specific state, like spin up or spin down, but is somehow inherent in the interactions themselves, in the type of measurements you can perform, and how the results link over time.
Okay, let's back up a bit then and set the stage properly. Why are physicists even thinking about emergent spacetime in the first place? Isn't space just, well, space, the thing we move through?
Well, for a long time in physics, yes, that was the view. Space and time were treated as the fixed, absolute, unmoving background. Think of Newton's laws. They happen in space, over time. Even standard quantum mechanics, in its usual formulation, assumes a pre-existing space-time stage.
Right.
Einstein's general relativity, of course, changed things dramatically. It made space-time dynamics, something that can bend, warp, ripple, that's gravity. But even in GR, space-time is still treated as a fundamental entity, a kind of geometric manifold. The real problem, the crack where these ideas start to seep in, arises when you try to reconcile general relativity with quantum mechanics.
The old unification problem.
Precisely. When you try to quantize gravity, to describe space-time itself using quantum rules, especially the incredibly tiny Planck scale where both quantum effects and strong gravity should be significant. Well, our current theories tend to break down. You get infinities, paradoxes, inconsistencies.
So our best theory of the large, gravity, and our best theory of the small, quantum mechanics, don't play nicely together when it comes to the fabric of space-time itself.
That's a good way to put it. They fundamentally clash at those extremes.
Yeah.
And this persistent failure has led many researchers to suspect that maybe we're asking the wrong question. Maybe space and time aren't the fundamental components we should be quantizing.
Maybe they're symptoms of something else.
Maybe they are emergent phenomena, arising from a deeper, more fundamental theory that doesn't necessarily involve space or time at its core. Think back to the temperature analogy.
From the atoms.
Right. No single atom has a temperature, but a large collection does. Temperature emerges from the collective statistical behavior of countless atoms. The idea is similar for spacetime. Perhaps it emerges from the collective behavior or the entanglement patterns, or the relationships between more fundamental, possibly non-spatiotemporal entities or degrees of freedom.
So it's like the universe's operating system isn't written in space and time, but space and time are like the graphical user interface that emerges from the code.
That's actually a pretty decent analogy.
Yeah.
Yeah. And the paper we're looking at references this broader trend in theoretical physics, mentioning ideas from string theory or the holographic principle, which also suggests that the spacetime we experience might be, in some sense, an approximation or a projection from something more basic.
Okay, so against that backdrop of trying to find a deeper reality, this paper by Fullwood and Vedral offers a very specific proposal. Not just space-time is emergent, but a potential mechanism for spatial emergence, linking it directly to these quantum temporal correlations.
That's right. They're moving beyond the general philosophical idea of emergence and proposing a concrete, mathematically grounded mechanism for how specifically 3D Euclidean space could arise. And they tie it to this very specific aspect of quantum mechanics. The relationships, the correlations between sequential measurements performed on just one single quantum system over time.
It sounds almost too simple. What are the core ingredients they use in their recipe for emergent geometry? You mentioned a single qubit.
They really do start with something remarkably simple.
Okay.
And that's part of the elegance, I think. The key ingredients are basically fourfold.
Okay.
First, as you said, a single qubit. That's the simplest possible quantum system that shows non-trivial quantum behavior. It's like the quantum version of a classical bit, which can be 0 or 1, but a qubit can be in a superposition sort of both at once, and its state is described mathematically by a vector in a two-dimensional complex space called a Hilbert space.
Got it. Ingredient one qubit.
Ingredient 2, sequential measurements. This is absolutely crucial. It's not about measuring the qubit just once and getting an answer. It's about performing measurements one after another at different points in what the observer experiences as time t1, then t2, then t3, and so on.
The temporal part of temporal correlations?
Precisely. Ingredient 3, the type of measurements. They focus specifically on a class of measurements called polyobservables. For a qubit, these correspond physically to measuring the spin of a particle, like an electron, along specific spatial axes, think x, y, or z. Mathematically, they're represented by the famous Pauli matrices, sexy, pulses, along with the identity matrix.
Okay, so specific kinds of questions you can ask the qubit.
Yes. Think of them as probing the qubit's properties in these three distinct orthogonal directions. And ingredient 4, the correlations in time between the outcomes of these sequential Pauli measurements. How does the result of measuring, say, spin along the x-axis at time t1 influence or relate statistically to the outcome of measuring spin along the axis at a later time t2? That relationship is the correlation.
So putting it all together, the central hypothesis is that these temporal correlations, derived specifically from doing sequential Pauli measurements on just one qubit, uniquely reveal the mathematical structure of 3D Euclidean geometry.
That's the core mathematical claim they set out to prove in the paper. They aim to show that these correlations aren't just some abstract quantum property floating around, but they actually, mathematically, are the Euclidean structure. They exactly mirror it.
And you mentioned earlier something really striking about this connection, the independence from the qubit's initial state. Can you expand on why that's such a big deal? Why is that so counterintuitive in quantum mechanics?
Right. So in standard quantum mechanics, the probabilities of getting different measurement outcomes are almost always entirely determined by the system's quantum state right before the measurement is made.
Makes sense. What you measure depends on what's there.
Exactly. If you measure the spin of an electron along the z-axis, the chance of getting spin up versus spin down depends entirely on the electron's state vector just before you measure. And then, crucially, the measurement itself generally changes the state, the famous collapse of the wave function. So if you make a second measurement right after, the probabilities for that second measurement depend strongly on the state the system collapsed into after the first measurement.
So the history matters. The first measurement affects the second.
Absolutely, which means correlations between sequential outcomes are typically highly dependent on the state the system started in before the first measurement. The whole sequence of probabilities depends on that initial.
But this paper finds that for these specific measurements, sequential Pauli measurements on a qubit, the correlation structure somehow doesn't depend on that initial.
Precisely. That's the kicker. For the specific two-time correlation function they define and calculate, they demonstrate that when you plug in pairs of Pauli observables, the final result is the same no matter what the initial state of the qubit was. It could have been spin up, spin down, some weird superposition The resulting correlation value is identical.
That is weird. How can the relationship between outcomes be fixed if the starting probabilities change with the state?
It has to do with the specific algebraic properties of the Pauli matrices and how they interact with the projection operators involved in the measurement update rule.
Yeah.
The state dependence, which is certainly there for the individual measurement probabilities, effectively cancels out when you compute this specific two-time correlation function for pairs of Pauli observables. It's a remarkable mathematical feature of this particular system and these particular measurements.
Okay, so mathematically it works out. But what's the implication of this state independence, especially for this grand idea of geometry emerging?
It's absolutely crucial. It's perhaps the most critical element for making their hypothetical model of an observer plausible, which we'll get to later. Think about it. If the temporal correlations depended strongly on the Qubit state, an observer trying to extract geometric information from these correlations would be in a terrible position.
Why?
Because the Qubit state might be unknown or constantly fluctuating. The observer would need to constantly figure out the state, maybe re-prepare it in a known state before each measurement pair, or average results over countless different initial states to maybe wash out the dependence. It'll be incredibly complex, maybe impossible in a realistic scenario.
Right, the geometry they measure would keep changing depending on the Qubit's mood, so to speak.
Exactly. But because, as the paper proves, the correlation is state-independent for Pauli measurements, the geometric information is reliably, consistently present in the correlations of any sufficiently long sequence of these measurements. Regardless of the Qubit's specific quantum configuration throughout that sequence, the observer doesn't need to know or control the state.
So the geometry isn't a property of the state, but a property of the measurement interactions themselves.
Yes, it's a fixed property of the structure of the Pauli observables and how they relate to sequential measurement on this simple Qubit system. The state independence ensures that this structure is robust and accessible. It's always there to be found in the correlations, waiting to be extracted.
That makes a lot more sense. You wouldn't want your definition of space itself to be flickering in and out of existence based on the quantum state of some random qubit you're probing.
Precisely. If geometry is to emerge, you'd expect it to be a more fundamental, stable structure, independent of the specific goings-on of the system being used to reveal it. This state independence provides that stability.
Okay, that really sets the stage for why this idea, while seemingly simple in its ingredients, is actually quite deep and potentially powerful. Now let's dive into the mathematical heart of the paper, section 2. The mathematical engine where they formally define things and present their main theorem. They start, as you mentioned, with the standard language of quantum mechanics.
Right. Standard stuff for anyone familiar with quantum theory. You have a finite-dimensional quantum system. Its state lives in a complex vector space called the Hilbert space. Let's call it HA. And the things you can measure, the observables, are represented by mathematical objects called Hermitian operators acting on that Hilbert space,
And these operators have real eigenvalues.
which correspond to the possible numerical outcomes you can get when you perform the measurement. So Hilbert space is the abstract state space, the arena where the quantum state resides, and the operators are like the tools you use to poke the system and get information out.
Poke the system. I like that. Okay, so within the standard framework, they introduce a special concept, the ghost space. What exactly is that?
Okay, so a ghost space, which they denote S, is a specific type of collection of these observable operators. First, it's a real linear subspace. That just means if you take any two observables that are in the special set S, say O1 and O2, then any real linear combination, like A01 plus B02, where A and B are real numbers, is also an observable within that same set S. It's closed under real linear combinations.
So it's a well-behaved mathematical space of observables.
Yes, but the really crucial defining property comes from its basis. A guess space has a basis, a sort of fundamental set of building block observables within it. Let's call them OI, like O1, O2, O3, that satisfy a very specific algebraic relationship.
The equation.
The equation. It is OI OJ plus OJ OI equals 2 day 1.
Okay, let's unpack that carefully. OI OJ means applying operator OJ, then operator OI. The left side, OI OJ plus OJ, is often called the anti-commutator, sometimes written OI OJ.
Correct. It captures a symmetric combination of applying the operators in different orders.
And on the right side, 2 day 1. Let's break that down. OJ is the Kronecker delta symbol.
Yes, it's a very simple object. Doj is equal to 1 if the indices I and j are the same, OIJ, and it's equal to 0 if the indices I and j are different.
The 1 in the equation.
That represents the identity operator. The operator that does nothing leaves any state unchanged.
Okay, so the anti-commutator OI equals 2 times the identity if aaj, and it equals 0 if ij. What does this tell us about the basis observables OI themselves? Let's take the first case, I, uj.
Right. If IOJ, then I becomes I, which is 1. So the equation simplifies to AAOI plus OIOA equals 211. That's 2OI2 equals 21.
Divide by 2 and you get OI2 equals 1. The square of each basis observable is the identity operator. What does that mean physically?
An observable O who squares the identity operator, O2 equals 1, has a very specific property. Its eigenvalues, the possible outcomes of measuring it, can only be +1 or -1.
Ah, the 181 outcomes you mentioned earlier.
Exactly. These are often called dichotomic observables because they only yield 2 possible results. The paper mentions this explicitly in their proof section. When you measure such an observable, the system state gets projected onto either the subspace corresponding to the +1 outcome or the subspace corresponding to the -1 outcome. So all the fundamental building blocks of a guess space correspond to these simple yes-no 1-1 type measurements.
Okay, that's the ij case. What about when I is not equal to j?
If I Secchi, then the Kronecker delta Dodge is 0. The right side of the equation becomes 2, 0, 1, which is just 0, the 0 operator. So for different basis elements, the equation reads OI-OJ plus OJ-OI equals 0.
The anti-commutator is 0. What does that mean?
It means that OI and OJ anti-commute. If you swap their order, you pick up a minus sign. OI-OJ equals OJ-OI. They have sort of mutual incompatibility when applied sequentially in this specific algebraic sense.
So summarizing the ghost space definition, it's a linear space of observables built from a basis set where each basis element gives 1 outcomes, OI-2 equals 1, and any 2 different basis elements anti-commute, OI-OJ or 0 for ij.
Precisely. And this algebraic structure, OI2 1 1 and OI-OB 0, isn't just some random mathematical curiosity. It's deeply connected to geometry. The paper points out that this is exactly the defining relation for the generators of a real Clifford algebra, specifically CLRD.
Clifford algebra, that sounds familiar from geometry contexts.
It is. Clifford algebras provide a powerful way to encode geometric concepts like rotations and reflections algebraically. A ghost space of dimension d provides a representation of the Clifford algebra associated with a d-dimensional Euclidean space, RDJD. So the very definition of a ghost space already contains a hidden link to Euclidean geometry. It's baked into the algebra.
That's fascinating. So the connection to geometry starts right there at the definition level. And what's the prime example they use throughout the paper?
The key example, especially relevant for the simplest quantum system, the Qubit, whose Hilbert space is two-dimensional, is the space spanned by the 3 Pauli spin matrices, Sex, Sovlanges, Clis. These 3 matrices, plus the identity matrix, form a basis for the space of all 2x2 Hermitian operators. But specifically, Sux and Sux themselves form a basis for a 3-dimensional ghost space.
Let's check if they fit the definition. Do they square to the identity?
Yes. Sux by 2, Sus2 is 1, the 2x2 identity matrix. So they represent dichotomic observables giving 1 outcomes corresponding physically to spin up down along each axis.
And do different Pauli matrices anti-commute?
They do. For instance, Sux equals pions, while Success is a 0. The same holds for the pairs. They perfectly satisfy the ghost space conditions for D3. This specific 3-dimensional ghost space, spanned by the Pauli matrices, is what they call Pauli in the paper. It's the mathematical structure describing spin measurements in our familiar 3 dimensions.
Okay, so we have this special type of observable space, the ghost space, perfectly exemplified by the 3D Pauli matrices for a qubit. And we have the concept of sequential measurements over time. How do they formally connect these two ideas to calculate the correlations?
They define what they call the two-time correlation function, which they denote EO0102. This function is designed to precisely quantify the statistical relationship, the correlation, between the outcome you get when you measure observable O1 at time t1 and the outcome you get when you subsequently measure observable O2 at a later time p2 t1. And this is calculated assuming the system started in some initial state before the first measurement.
How is it calculated? What goes into that E function?
Well, the standard quantum mechanical way to calculate this kind of sequential correlation involves considering the first measurement, O1. Let's say O1 has possible outcomes. O, which would be O1 if O1 is in the goose space. For each possible outcome O, there's a certain probability of getting it, which depends on the initial state. Getting outcome OI also projects the system's state into a new state associated with that outcome. Let's represent this projection with an operator pi. Then you need to calculate the expected value, the average outcome, of the second measurement, O2, but calculated in this new state that resulted from the first measurement.
Okay, so it's like for each way the first measurement could turn out, find the state after that outcome, pi applied to a, then find the average result of O2 in that state, and finally average all of those results, weighted by the probability of getting MUI in the first place.
Exactly. It's a weighted average reflecting the two-step process. The mathematical formula they use captures this precisely. EO1O2, EIETR, pi O pi O2. The trace operation TR is how you calculate expected values in quantum mechanics. Pi O pi represents the unnormalized state after getting outcome me, and EO carries the weight corresponding to that outcome value. This E function intrinsically encodes the temporal dependency, how the first measurement and its outcome influence the expectation for the second.
It sounds quite involved compared to just measuring two things simultaneously.
It is. And importantly, this sequential definition is generally not symmetric if you swap O1 and O2. Unlike simple correlations, the time ordering matters. And this specific structure is what allows it to potentially behave like an inner product, which is key for geometry.
Right, so now we arrive at the main event, the linchpin of the paper. Theorem 1. What does this theorem definitively state and prove?
Theorem 1 is the mathematical powerhouse of their argument. It establishes a very strong equivalence. It states, a real linear subspace S of observables, acting on some Hilbert space HA, is a ghost space IF and D only F for every possible initial state of the system, the two-time correlation function EA. When calculated for pairs of observables O1 and O2 taken from within that subspace S, satisfies two conditions. First, it defines a real inner product on the space S. Second, and crucially, this inner product structure is completely independent of the initial state.
Okay, if and only if. That's a powerful statement in mathematics because it works in both directions. Let's break it down. First direction. If you start with a space of observables S that you know is a ghost space, like the Pauli space for a qubit.
The theorem guarantees that the two-time correlation function EA, calculated between any two observables in that space S, will automatically behave like a real inner product, and the result will be the same regardless of the initial state.
So the ghost space structure causes the temporal correlation to be a state-independent inner product. What does that look like explicitly for the Pauli case?
This is one of the main technical calculations in the paper. They take two general observables from the 3D Pauli space. These can always be written in the form O1, show RVS, and O2 equals SE, where R and S are ordinary three-dimensional real vectors, and Sarah represents the vector of Pauli matrices. So RS means Rx plus Russi plus Rs. They plug these into the definition of E, O1, O2, using the specific Pauli matrices and the measurement projection rules for a qubit.
And what comes out after crunching through the quantum mechanics?
After a calculation involving traces of matrix products and summing over the Riemann outcomes, it simplifies dramatically. They find that E, R, R, E, S.
Wow. Wait. The complicated two-time quantum correlation function E, which involve the initial state, the measurement projections pi, the eigenvalues are E, all of that machinery, just boils down to the simple standard Euclidean dot product of the vectors R and S that define the observables. Exactly. That's the stunning result for the Pauli space. And remember, the theorem guarantees this result holds for any initial state. The dot dependence completely vanishes in the final answer, leaving only the geometric dot product RS. And the dot product is the heart of Euclidean geometry, right? It defines everything. Absolutely. The dot product RS gives you the fundamental geometric relationships. If you take the dot product of a vector with itself, you get the square of its length, RE, R2. And the dot product between two different vectors, RES, allows you to find the angle between them using the formula cos, RES, RES. So this result, RES, establishes a direct quantitative identity. The quantum temporal correlation is the Euclidean geometric structure for these observables. That's incredible. It's not just analogous, it is the metric.
The structure of 3D space is literally encoded in, or maybe even is, the pattern of these temporal correlations for Pauli measurements on a qubit. That's the powerful implication of this direction of the theorem. It shows how Euclidean geometry naturally emerges from the quantum dynamics of sequential measurements within this specific algebraic structure, the ghost space.
Okay, that's the IS is a ghost space, then E is a state-independent inner product part. What about the other direction, the only F part? That sounds like it's about uniqueness.
Yes, the only IF part is just as significant, maybe even more so in some ways, because it establishes uniqueness. It says, if you have any real linear subspace of observables S on some system A, for which you find that the two-time correlation function E happens to define a real inner product on S, and this inner product structure is independent of the initial state for all possible states, then that subspace S must necessarily be a ghost space.
So you can't get this nice state-independent inner product behavior from temporal correlations unless your observables already have that specific O-space algebraic structure.
Though I too pay 108 always do that. Precisely. It proves that the ghost space structure is the necessary condition. If you observe state-independent inner product correlations emerging from sequential measurements, you know you must be dealing with observables that form a ghost space.
And what does that imply specifically for a single qubit system?
For a single qubit, a two-level system, the space of traceless Hermitian operators, which includes the Pauli matrices, is three-dimensional. The theorem, combined with known results about representations of Clifford algebras, implies that the three-dimensional Pauli space is essentially the unique subspace of observables on a qubit whose two-time correlations exhibit this state-independent real inner product property.
So it's not just a way to get Euclidean 3 geometry from qubit correlations.
It seems to be the way, at least through this mechanism of state-independent two-time correlations. The Pauli space is uniquely singled out on the qubit side, and correspondingly, Euclidean 3 space is the unique geometric structure that emerges on the correlation side via this specific process. It establishes a unique two-way link.
That makes the finding much stronger, doesn't it? This isn't just a coincidence or one possible construction among many, but something perhaps more fundamental about the relationship between qubit measurements and 3D space. The paper does mention that while other aspects of qubit state geometry, like the block sphere or temporal correlations, have been studied before, this specific connection, linking the two-time correlation function E itself directly to the Euclidean metric and proving its state independence as the defining feature of WIP spaces, was not previously established or fully appreciated.
That seems to be their key contribution, yes. People knew the state space of a qubit, the block sphere, looks like a 3D ball, which obviously has geometry. But this paper argues the geometry isn't just in the static state space. It actively emerges from the dynamics of sequential measurements over time, specifically from their correlations. And the state independence is the crucial property that makes this link robust and directly equates the correlation function with the metric RS, independent of the system-specific state. That connection seems to be novel.
Okay, this mathematical theorem is clearly powerful, but it's still quite abstract. How do the authors then bridge this mathematical result to a more tangible, albeit hypothetical, physical scenario? This brings us to section 3, the hypothetical model building space from correlations.
Right. This is where they move from the rigor of the mathematical proof to a conceptual model, a sort of toy universe thought experiment. They want to illustrate how an observer, equipped only with the ability to perform these measurements, could potentially experience or construct Euclidean geometry based entirely on the principle established by Theorem 1.
What does this toy universe look like?
It's incredibly minimal. They imagine a universe containing only two entities, an observer and a single qubit. And here's the absolutely critical starting assumption. There is no pre-existing spatial background.
No stage, no arena.
None. The observer is not conceived as being located in space, nor is the qubit placed at some location. Space itself is what's supposed to emerge.
So what does the observer have?
The observer is assumed to have two things. First, a subjective sense of time and ability to order events sequentially. This happened, then this, T1, T2, T3. Second, the observer possesses a probe.
A probe.
Yes, some kind of device or capability that allows them to interact with the qubit by performing measurements on it. The outcomes of these measurements, +1 or -1 in this case, are the observer's only source of information, their only sensory data about the qubit, and indeed about anything external to their own sense of time.
Okay, an observer with time and a probe. What's the crucial assumption they make about this probe? What can it do?
They assume that the set of possible measurements the observer can choose to perform using this probe corresponds precisely to the Pauli observables, the three-dimensional Qubit Pauli we discussed. This means the observer can effectively ask the qubit questions corresponding to what is your spin along direction R for any 3D vector R by applying the operator R.
So the observer's interaction capabilities are hard-coded to match the structure that Theorem 1 identified as geometric.
Exactly. The observer's sensory apparatus is tuned to the Gies space Pauli. The qubit itself isn't thought of as being in space. Rather, it acts as a kind of abstract reservoir of quantum information. The geometry isn't a property of the qubit's location, but rather a property of the information structure accessible through these specific Pauli measurements over time.
So how does the observer, starting with just this stream of +1 and -1 outcomes over their personal time, actually come to perceive or construct the 3D geometric structure? How do they get from a list of measurement results to concepts like distance and angle?
Okay, let's walk through the process they envision. Imagine the observer decides to perform a very long sequence of n measurements on the qubit at successive times, t1, t2, t3, up to tn. At each time step t, the observer chooses a particular Pauli observable to measure, say 1 corresponding to the direction vector v, resulting in the operator ATS. They perform the measurement and record the outcome, let's call it eddy gas, which will be either +1 or -1.
So they end up with a long, long list, by 1, by 2, by 3, xn, just plus and minus ones. How does geometry emerge from that?
The key, again, lies in looking at the temporal correlations, specifically between consecutive measurements in this long sequence. Consider the product of two sequential outcomes, x, xi plus 1. This simple product, +1 plus 1 plus 1 plus 1 plus 1, etc., turns out to be directly related to the two-time correlation function s.
How so?
Let's say the observer decides to repeatedly probe the relationship between two specific abstract directions, represented by vectors r and s. They might, for example, set up a pattern where they measure the observable O1 and the observable O2 at all even time steps, T2, T4, T6.
Okay, an alternating sequence.
Right. Now consider a consecutive pair of outcomes in this sequence, say xi and xi plus 1. Their product, xi plus 1, represents a single sample contributing to the overall correlation between measuring O1 and then O2, or O2 then O1, depending on whether it is odd or even. Now here comes the crucial part, invoking Theorem 1.
The state independence.
Exactly.
Theorem 1 told us that ER, US, US, and this result is independent of the state before the first measurement in the pair. This means the expected correlation between any consecutive pair of measurements, corresponding to US, is fixed at the value RS, regardless of what the qubit state happened to be just before time t. It also means the correlation is independent of which pair in the sequence you look at, i.e., independent of the specific time index I, as long as n is large.
And why is that independence so vital for this hypothetical observer?
Because the observer in this minimal universe doesn't know the qubit state, and they likely can't re-prepare it in a specific state between each measurement. They are just passively probing whatever state the qubit falls into after the previous measurement. The state independence guarantees that despite this lack of control and knowledge, the underlying geometric correlation is still present and consistent in the relationship between any two consecutive measurements of Rs and S.
Okay, so the signal was consistently there, hidden in the noise of individual one outcomes. How does the observer extract that signal?
By averaging. If the observer performs this alternating sequence for a very large number of steps n, they can simply calculate the average of all the products of consecutive outcomes. Average 1n1 and 1n1. Because each product, line xi plus 1, statistically fluctuates around the true correlation value, Rs, the law of large numbers tells us that for very large n, this calculated average will converge to the expected value.
And the expected value is?
The expected value is the two-time correlation function ERSS, which Theorem 1 proved is equal to Rs.
So simply by performing a long sequence of alternating measurements corresponding to abstract directions R and S, and then averaging the products of consecutive plus 101 outcomes, the observer can empirically determine the numerical value of the Euclidean dot product Rs.
That is precisely the core mechanism of emergence proposed in this model. The dot product, the fundamental building block of geometry, isn't assumed or given. It is extracted operationally from the statistical patterns discovered within the observer's temporal stream of simple measurement data.
And once the observer can calculate the dot product Rs for any pair of directions R and S they choose to probe,
they have everything they need to reconstruct the full Euclidean geometry of the three-dimensional space, defined by these possible probe directions. For instance, how would they determine the length or norm of a direction R?
Well, length squared is the dot product of a vector with itself. Ur2 equals R.
Right. So the observer would just repeatedly measure the same observable O AXI plus 1 at consecutive time steps t and ti plus 1. They'd calculate the average of the products AXI plus 1 over a long run. This average will converge to E, which equals RER. The observer takes the square root of this average, and voila, they have experimentally determined the length or O associated with that probe setting.
And angles between different directions, say R and S.
Same principle. They first determine the lengths R and S using the method we just described. Then they perform the alternating sequence and calculate the average correlation, which gives them the value of Rs. Finally, they just plug these experimentally determined numbers into the standard cosine formula. S is RES. This gives them the angle between the abstract directions R and S that their probe can access.
That is actually quite incredible when you walk through it. The observer, starting with essentially nothing but a sense of before and after, a simple qubit, and a probe capable of Pauli measurements, can literally build up the entire metric structure, lengths, angles, orthogonality of Euclidean 3 space, just by analyzing the patterns in the sequence of plus ones and miss ones they record over time.
Yes. The geometry emerges as the robust, state-independent pattern inherent in the temporal correlations of their interaction with the qubit's quantum information. The 3D space isn't a pre-existing stage they discover. It is the structure of correlations they find, the structure revealed by their sequential probing over time.
And the paper emphasizes that this emergence is tied specifically to the probe measuring Pauli observables, agua space. What if the probe measured something else?
Well, according to Theorem 1, specifically the only if part, if the observables measured by the probe did not form a Go space, then the resulting two-time correlations, would not yield a state-independent inner product. The correlations might be state-dependent, or they might not satisfy the properties of an inner product at all. In either case, the simple averaging procedure wouldn't reliably extract a consistent Euclidean dot product. The structure that emerged from the correlations, if any, would likely be different, perhaps non-geometric or state-dependent. This reinforces the uniqueness finding from the mathematical section. The Pauli Go space seems uniquely tied to Euclidean 3 geometry via this mechanism.
And again, the state independence provided by the Go space structure was absolutely paramount for this whole hypothetical scenario to work, right? Because it meant the observer could just keep probing without needing to reset or even know the qubit's state.
Exactly. It makes the proposed mechanism for emergence potentially feasible, even for a very simple observer operating in this minimal conceptual universe. They don't need complex control, just persistence in probing and pattern analysis.
Okay, this paper lays out a really elegant, if perhaps surprising, mathematical connection and a compelling hypothetical model for how space itself might emerge. Let's move towards wrapping up with Section 4. Looking ahead, synthesis and open questions. What are the absolute core takeaways, and where does this line of thinking potentially lead?
I think the core finding, the central message that is truly striking, is the establishment of this unique, mathematically rigorous, and state-independent correspondence. It shows that the structure of temporal correlations, specifically the two-time correlation function E, resulting from sequential Pauli measurements on a single qubit, is identically equal to the Euclidean metric, the dot product, S, on the three-dimensional space of those Pauli observables.
It's not just an analogy, it's a mathematical identity. E-R-A.
Precisely.
Right.
And the linchpin that makes this identity so powerful for the idea of emergence is the state independence. That's the second key takeaway. This geometric information, encoded in the correlations, is robust. It can be extracted by an observer simply through sequential probing over time, without needing any knowledge or control over the qubit-specific state.
Which connects to the third takeaway. The qubit acts as a kind of minimal reservoir of quantum information,
from which the structure of 3D Euclidean geometry can be distilled purely through analyzing the temporal patterns of interaction, regardless of the qubit's internal fluctuations.
So it's a concrete model for emergence from quantum information dynamics, but it feels like just the first step. The paper focuses on 3D space. Our reality, as we understand it from relativity, is space-time. What are the big challenges or open questions in trying to extend this idea to encompass the full four-dimensional space-time metric?
That's a huge open question and probably the most immediate and significant one. This paper provides a mechanism for the emergence of the spatial part of the metric. Time, in their model, is treated differently. It's the observer's external subjective parameter that orders the sequence of measurements T1, T2, T3. It's not part of the emergent structure itself in the same way space is.
So how would you get time integrated into the geometry?
That's the challenge. To get a full space-time metric like the Minkowski metric of special relativity or the curved metrics of general relativity, you'd need the temporal dimension to be treated on a more equal footing with the spatial dimensions within the emergent structure. This would likely require a more sophisticated framework, perhaps considering correlations across more than just two time points, or maybe using different types of quantum systems or observables, or developing a different mathematical formulation for quantum observables over time. It's not clear how to make that leap from emergent space with external time to emergent spacetime. It's a non-trivial conceptual and mathematical step that this paper doesn't address.
And then, even if you could get spacetime, there's the elephant in the room, gravity. General relativity tells us gravity is the curvature of spacetime. If geometry itself is emerging from these quantum correlations, how could curvature possibly arise within this picture?
That's the other massive challenge, isn't it? Gravity, in Einstein's theory, arises from the presence of energy and momentum, which warp the space-time manifold. In the model presented in this paper, the geometry is a structure defined on the abstract space of the Pauli observables. How does curvature on that space of observables relate to the physical presence of mass or energy? Does gravity emerge from the collective behavior or interactions of many such qubits, perhaps entangled in complex ways? Or does it require incorporating different kinds of quantum fields into the picture?
It seems like a very different way to think about gravity, not as curving a pre-existing manifold, but as perhaps modifying the correlation structure itself.
Possibly. Or maybe the correlation structure is the manifold, and its properties change. This paper provides a mechanism for generating flat Euclidean 3 space from the simplest case. Extending this framework to incorporate the curvature described by general relativity is a monumental leap, requiring fundamentally new ideas about how matter and energy couple into this emergent geometric structure. It's wide open.
The authors do briefly hint at potential future directions, mentioning ongoing research into concepts like quantum observables over time. Does that offer a path forward?
It might. That area of research tries to develop formalisms for describing how quantum properties evolve and can be measured continuously or quasi-continuously over time, which could be more suitable for capturing the dynamics needed for an emergent space-time picture than just instantaneous measurements. It suggests that the mathematical tools required to describe the full emergence of curved space-time might involve more complex temporal correlation functions, perhaps involving integrals over time, or related structures that capture the system's continuous evolution and how it relates to geometry. It's speculative, but it points toward the kind of mathematical development that might be needed.
They conclude the paper with a really evocative analogy, don't they? Echoing Archimedes' famous lever quote.
Yes, it's a great summary. They paraphrase Archimedes. Give me a qubit for long enough and a probe in which to measure it, and I shall extract the geometry of our world.
What do you really take away from that final, bold statement?
I think it beautifully encapsulates the essence and the ambition of their finding. It highlights the almost absurd simplicity of the proposed starting ingredients, just a single qubit, the simplest quantum system, a probe capable of specific interactions, and the passage of time and contrasts it starkly with the incredibly profound and complex structure that they argue can be extracted, the very geometry of our familiar 3D world.
It's a statement of principle, almost.
Exactly. It's saying that potentially the most fundamental aspects of the physical reality we experience, like the structure of the space we move in, might not be fundamental themselves, but might instead be built from and revealed by the most basic units of quantum information and their dynamical relationships over time, accessed simply through the act of measurement. It's about finding the complex hidden within the simple, uncovering the geometric structure buried within the statistics of correlation.
Okay, so let's try to synthesize this for you, the listener. Stepping back from this deep dive, what are the big aha moments or key takeaways you should carry with you?
I'd say there are maybe 4 main ones. First, the core idea itself, that the space you perceive around you might not be fundamental, but could be an emergent phenomenon arising from a deeper quantum level. It challenges our most basic intuition.
Right.
Second, this paper offers a concrete, mathematically rigorous, and frankly quite surprising mechanism for how that spatial emergence could happen. Specifically, from the structure of temporal correlations between simple, sequential quantum measurements on a single qubit.
Geometry from timing.
Geometry from timing and correlation. Third, the truly remarkable finding of state independence. The fact that this emergent geometric structure is independent of the qubit's initial state makes it a robust property, something an observer could potentially extract just by interacting with the system over time, without needing detailed knowledge or control of its quantum state. That's crucial for plausibility. The uniqueness result. The theorem suggests that for a single qubit, the Pauli space and Euclidean 3D geometry are uniquely linked through the specific mechanism of state-independent two-time correlations. It's not just a connection, it appears to be the connection in this context.
So it takes these abstract quantum mechanical concepts, qubits, Pauli measurements, correlation functions, and suggests they could be the hidden source code for our most basic experience of physical reality, which fundamentally reframes how we might think about space itself.
It really does. It proposes that the familiar, solid feeling of 3D space could, at its deepest level, be a macroscopic manifestation of intricate patterns woven from the temporal relationships within quantum information.
Okay, so building on that, here's a final provocative thought for you to chew on after we finish. If the geometry of space itself can potentially emerge from the temporal correlations of quantum measurements, as this paper mathematically demonstrates is possible, could our own subjective experience of inhabiting a 3D reality be, on some profoundly deep level, the result of our brains, or perhaps our very consciousness, processing incredibly complex patterns of quantum correlations? Correlations happening constantly within our own physical structure and through our interactions with the environment.
That's taking the core idea of the paper and pushing it into some very deep, very speculative philosophical territory about consciousness and perception. But it certainly follows the chain of logic, doesn't it?
It definitely gives you a new, maybe slightly unsettling perspective on just navigating the room you're in right now. On that note, thank you for joining us for this deep dive into the potential quantum origins of geometry.